Nice to see you all. Thanks for joining us. Today we are going to talk about publication bias, and hope you will learn some new things as I've done when going deeper in this topic. And because there are a lot of ideas, I thought of I don't know, bringing some specific quotations about each of ideas we are going to talk and maybe discuss. Whenever you want, you can interrupt me and intervene. So I want to talk about poor methods get results. This is the first idea. The second one is part of the problem is that no one is incentivized to be right. The third one is statistical techniques for testing hypotheses have more flaws than Facebook privacy policies, and this idea of reproducibility crisis. So, beginning with the first one, I will, I don't know, present kind of question for you so we can see uh, what previous knowledge you have about it or if you have any idea about it. So, with each idea, I will ask you one question. So, if you want, please ask this question in the chat. So, why do poor methods could get results in scientific research? The first option is because there are not enough or clear guidelines for researchers. The second, because there are incentives for poor method usage. Third, because poor methods are the progeny of competitive researchers or labs, and all the above. So please, in the chat, if you can type A, B, C, or D. We have D. D also. Any other?
I'm struggling with this question because I'm not. I mean, what do you mean by poor methods? And is there any evidence? Is there any evidence that a lot of the research is using poor methods? Like, yeah.
Okay, so we are going to go deeper on it
Okay.
through the first idea. So yeah, it's a tricky question. It's a tricky one because also B and C are correct in the way the authors of the paper I worked for these presentations, Maldino and McElrath, this article titled "Natural Selection of Bad Science." They say about this. So they are proposing that mainly the the research institutions are uh, mm, are doing some incentivizing activities that that make poor methods to be used more and more, and these methods are going to be shared from one group of researchers that are now doing their activities to the project. So we are going to go deeper on it. So then we have to think about it in this in this approach of natural selection in general. So they begin this explanation with the natural selection process, and the natural selection, if we think it in the biology area or field, have three main assumptions. So the three main assumptions of natural selection is, first of all, variation. It has to be be variation between the species. So there has to be different groups of species that compete between them. Then the second assumption is that the variation have consequences for survival or reproduction. So different groups can survive better because of their characteristic than others. And the third one is that variation must be heritable. So some subgroups that survive, they will transmit to the next generations their characteristics. So that is the main idea of natural selection. Could we apply it to scientific methods? Well, we know that cultural activity it's also having this process of natural selection. So cultural, different cultural activities are naturally selected. Science is a cultural activity, and part of the science are scientific methods. So, is there variation in scientific methods? They are, of course, they are. They are different methods that we are using in science. These different scientific practices have consequences for survival or reproduction? Well, they actually have. Theoretically, we understand that because in our activities to go to go further and get some positions, some professional positions, we have to make publications. So mainly obtain highly competitive positions is based on publications, and those publications depends on the scientific practices. And third, this variation is heritable. Well, the apprentices or the mentees acquire the research habits and statistical procedures from mentors, peers, or other researchers that they consider more, I don't know, more knowledgeable in the field. So we can see theoretically that scientific methods have also this process of natural selection. Okay, so do you have any consideration by now? Do you have any idea about it? We can go on? Yeah?
Yeah, no, I thought it was very interesting. Yes, agree.
So part of the problem is that no one is incentivized to be right. So we just seen that scientific methods have this process of natural selection. And what is happening with the natural selection? Is there any incentivization for researchers to, I don't know, do or use some specific methods? Well, we have another question. Does the scientific environment incentivize any kind of scientific practices? Well, this question is more to see if you have any intuitive idea about it. Yes, I know them and their consequences. Yes, but I am not sure about them or their consequences. Or no, it doesn't. What do you think? So BC. A. So any other person in BC? Well, I hope to, because if you already know all of it, we don't need this. Okay, so let's see what we can discover. So when we are talking about incentivization for publication or for researching production, one can, I don't know, think that maybe researchers misunderstandings, or there are some intentional errors made by researchers that make this poor methods or that statistical methods that are not very useful. But what these authors propose is that mainly the institutional incentives makes that poor methods replicate. So the main idea is that every year there are a lot of PhD students graduating. So there are a lot of researchers every year, but there are not as many stable positions in the institutions for each of them. So it has to be a selection. It has to appear a selection of the different researchers. What do you think there are some criteria that institutions use to select researchers or PhDs? Mainly because of that idea of the beginning of their career. Do you have any?
Sorry, could you ask the question again? So how do universities choose?
Yeah. Which are the criteria that they use to choose different researchers for the positions they have?
Oh, publications. Number of
publications. So number of publications?
Number, and I think that's very important. Number of publications.
Any other idea?
Might also involve research plans.
research plans. Could be.
I think different quantitative metrics, there are a lot, like also, of course, it counts if you participated, not participated in certain projects, how many, what you organized, didn't organize, how many conferences, and so on. So I think it's quite a lot about singular numbers of different activities that is part of PhD, and a number overall picture. So I did a lot here, I did a lot there. So that makes you more strong candidate on average. Yes.
So in general, like production, no? So production of papers, production of projects, production of different kind of things related with the field. Well, these authors mainly identify two of them. One of them is innovative work. So institutions are incentivizing innovative work, and this can be seen in this data. So they have analyzed what were the frequency, or which was the frequency of words like innovative or groundbreaking or novel in PubMed abstracts between in the lapse of 40 years, 1974 to 2014, and the increase was 2,500% of these words. So innovative work seems to be one of the criteria they use. And the other one, of course, is the high amount of results. So the number of publications, the publications in highly recognized journals, etc. And well, the idea is that this criteria the institutions use have some consequences on the methods the researchers are using. So the first one is that positive results are more likely to be published than negative results. That is because mainly the usage of methods like p-values, like underpowered studies are generating this kind of results. We will go deeper on each of these consequences. Then there is an increase of false discoveries, both false positives and false negatives. Again, what it has been seen is that a lot of studies are underpowered. Third, there are more underpowered results. And fourth, little absence of replication studies, with each the main point we are discussing at the second part or at the end. Well, what can be concluded from this is that the findings that researchers have are propagating more amount than rigor. The third idea I want to discuss with you is that thing of statistical techniques for testing hypotheses have more flaws than Facebook privacy policies. We are going to see what's that referring to. Another question is, you have to say if this statement is true, false, or you are not sure. Statistical significance, for example, a p-value lower than 0.05, indicates a scientifically or substantively important relation has been detected. This is true. It's true for scientific environment, but false for scientific approaches. It's false, or I am not sure. Oh, sorry. What do you think? B. Okay, maybe you've done a trick here, because usually you have this clue of the larger the response that could be, because you took more time to elaborate that one. B and D. Another one, B and D. Okay. So C, false. Yeah, so it is false, and we are going to see why it's false. It's false in general, but seems that scientific environment take it as true because they are using this to publish. We are going to see it. So to explain this and hoping I'm not getting too much deeper in it, and also please just interrupt me and correct me because I am not a statistician and I am not an expert, but I am trying to explain you the main approaches to test to hypothesis test. So there are mainly two approaches to testing hypothesis, and this is the test of significance and test of acceptance. The test of acceptance is the approach of Neyman Pearson, which is the first one, and is this approach that we usually understand with the main hypothesis, the alternative hypothesis, what we do with both of them, what are the probabilities of rejecting the null hypothesis and being true and being false, etc. So, which is the main idea here? The main idea is that we have two distributions, which are the main hypothesis we are using. They use this name of main hypothesis to refer to the null hypothesis and alternative hypothesis to refer to the H1. We have these two probability distributions, and what we want to see is that the rejection of our hypothesis, the main hypothesis or null hypothesis, which is called also falsifying the hypothesis, is really accurate or not. So here appears two kind of errors, type 1 and type 2. Tatiana, you also talk about it in the last meeting, so I'm not going to really go more deeper on it. So we have type 1 and type 2, or false positive and false negative. The false positive is determined by alpha, is when we are rejecting the null hypothesis when it's really true. So we are saying that there's an effect and there is not. And we have the type 2 error, or beta, when we are not rejecting a false hypothesis. So we are saying there is not an effect and there is. If you can see in the representation, these two errors are not independent. So they are like in a trade-off relation. So when you are lowering one, the other one is increasing, and when you are increasing one, the other one is lowering. This is very important because, as far as we know, beta is the opposite of power is the opposite of beta. So the ability to find the true effect, and this beta could increase or lower down, considering also alpha. So when you are conducting a study with high power, so diminishing the beta, you are also increasing the probability of finding false positives, because this line is going more to the left. This is again very important for a later idea. And well, if we focus on this statistical power idea, the authors analyzed the power during the last 60 years, well, more or less, because the study was published in 2016, and they saw that statistical power didn't change. So the low power is stable all along the time. Then we have the other approach, which is the test of significance, the Fisher's approach. This is the where the p-values appears. So we are normally using an hybrid approach. We are normally taking the p-values and rejecting or accepting or saying there are true or false the hypothesis we are proposing, and this is an error. We can't really do that, taking in account or considering the statistical approaches. So what is a p-value? The p-value is the probability of our data, the data in our sample, considering a distribution of the null hypothesis. So we have the null hypothesis. For example, there are no results, there are no differences between two groups, and we have a distribution which we consider is normally distributed. So this is an assumption of this approach. So if the null hypothesis is normally distributed and we assume that it's true, the second assumption, which are the probabilities of our data to fall into that null hypothesis? If our data falls into that hypothesis, we can consider that our data is random, so it's by chance. And if we have the less probability that our data fall in the null hypothesis, then less chances that our data is by random explication. Okay, so that's the main idea. With this, we created some interesting conclusions in our studies that a p-value of 0.05 is the statistical significance, which is arbitrary, and there is just 5%, for example, risk of a false alarm. This is not correct, but what we really have to ask ourselves with our results is, what are the odds that a real effect exists? So the more implausible or the more extravagant our hypothesis, the greater the chance of false alarms. For example, imagine you are studying telepathy, or I don't know if the unicorns exist. So this is a really implausible hypothesis. So that kind of assessment of your hypothesis will give you information about the chances of having a false alarm or not, and not the p-value. So a better interpretation of p-value, for example, of 0.05, is that the discrepancy from the hypothesis prediction will be as large or larger than that observed no more than 5% of the time if only chance were creating the discrepancy. So my data will not fall in the null hypothesis in the 5% of the times. That's the main idea. Well, we just cover an important topic. You have here an interesting representation of all of the idea of p-value, which I took from this article of Nuzo published in Nature. I really recommend you this article because it's only 3 pages and really explain very, very well these ideas of p-values. So at the bottom you have the probability of the results to be true. That is accounting plausibility taken for previous studies. So the probability of if we have the probability to find a real effect of 5%, and we have a p-value of 0.05, our chances of finding a real effect with a significant p is 11%. So it really depends on what you are proposing. What are your hypotheses? Okay. Well, we are going through the last idea or point. Do you have any consideration? Yeah, please. Joe?
No, I was just going to ask if anyone has any questions or whether that makes sense. So it's kind of saying like, it's not about a 0.5%. It really depends on what, how likely something is that you're looking for, right? I assume that then links back to issues around your population and sample and power, for example, because and that's probably why we should measure power as well as significance in our studies, right? Is that just I don't know if you want to go into that a little bit, but I think it's important because the problem with the p-value is not only the p-value, it's the fact that we need to look at other indicators of what the likeliness is of the effect.
Yeah, exactly. Exactly, because the Fisher approach doesn't propose an alternative. So it's just if our data is fitting to the null hypothesis or not. but is not proposing other alternatives. So that indicators of power and that could be very useful. Yeah, Tatiana.
I just wanted to add that it so nicely links to the previous talk we had, and and to me, I think the main message from these ideas is that we shouldn't blindly trust some number. This is, I think, the point. So we need always to consider different inputs and what is the situation overall in terms of bias, in terms of statistical power and other things, and then evaluate it all together, but not like, okay, I got this number, work done, perfect, I make like strong claims and conclusions. I think this is the main general message, at least I
Yeah, definitely. Also, when I was looking at this, I also look at some of my data because I'm doing a meta-analysis, and I have an analysis with a moderator, which is kind of interventions on specific motivational factor, which are the effects on other motivational factors and on achievement. And I have a difference between them of 0.3, an effect of 0.3 G, and it's not significant. It's a 0.4 or something like that, but it's a 0.3. So I have to go deeper on that data, but just using the p-value, I think it's not very adjusting to the data.
But it goes back, I mean, because yeah, so the main point is that publications are hung up to this, is it significant or not, right? That's kind of the publication bias, right? Is this focusing on 0.5, but as you said, there are other indicators of what's happening to data. And actually, you know, I think it's equally important to publish non-significant findings. And I know journals won't always take them. They will with pre-registration now, but there is an issue there. I really think, you know, what you mentioned there, and you know, we need to look at other indicators. I don't know if any one of you uses Bayesian analysis, for example, because that's the alternative to Fisher, right? Is using Bayesian analysis. Not sure if any of you are familiar with those.
A little bit, but I've never used it in practice.
A little bit.
So this is where I would suggest that if you come, so Bayesian analysis is that it doesn't just, you're not assessing this likeliness. You're actually assessing whether your actual hypothesis is true. So you don't go back to this null hypothesis. So it's a more direct measure, and it gives you the likeliness of how likely it is that there is, for example, a difference. So if you say, so in traditional statistical analysis, you would say, okay, I'm looking for a difference in my two groups, for example, or my two conditions. Then your null hypothesis is assuming that there isn't a difference, right? And that's the modeling of the p-value, that, you know, you're modeling your chances of that being true. So in Bayesian analysis, you assess whether that's directly the case or not. So what is the likeliness that your samples are very similar, for example? So if you've got very small sample sizes, or if you've got you get on this, like, you know, you're not quite sure with the distributions, because again, we haven't even spoken about distributions being issues as well. Then Bayesian analysis can help you with that. I'm not an expert on Bayesian analysis, but more and more I'm convinced that for certain questions, so when people say like, oh, I assessed whether my two groups are similar in age and I've done a t-test, right? And there is no significant difference between my two groups because the p-value is larger than 0.05. That doesn't mean that your two groups are the same. It just means that the two models, you know, it's about chance levels that you're talking about. And in those cases, you actually want to use Bayesian analysis to actually show how similar your two groups are, and directly assess the null hypothesis, if it were. So it's important to look at this. But I think what Madeline, what you nicely highlighted is because even if you would put your p-value at 0.001, which some people do, right? Or in medicine, for example, it's 0.001, the problem remains the same. The problem remains this focus in publishing on having a particular cutoff point, right? Where we kind of accept
that's it.
something is significant or not.
Yeah, I was just also going to add that this is related, as you said, with publication bias, because there's this kind of conclusion. So if I have a result significant with a p-value of 0.001, then it's a positive result. We can reject, and the null hypothesis is false, so we have a positive result, and that's not really the conclusion we can take from it. So that's why these kind of p-hacking activities have proceeded to more publication, and that's why it really helps the publication bias.
Is everybody familiar with p-hacking? Yeah, no. So do you want to explain p-hacking, Madeline?
Yeah, so it's like the activity of chasing to obtain the p-value you want to obtain. So maybe you are going to change your methods, you are going to establish your hypothesis a posteriori, or you are going to adapt some statistical analysis so you can obtain the p-value. Also, you can do 100 analyses and take only the ones who are significant. I think so. This is the definition.
Yeah, no, that's absolutely right. And it's bizarre that students do this, right? So not only students, but there's people in the past definitely done it. Like, oh, let's just analyze the data and then I see what sticks. If you throw enough analysis at the wall, one thing will come back significantly. If nothing comes back significantly, maybe we can randomly exclude some participants because that kid wasn't really paying attention very well, and maybe that kid was a bit of an outlier and it didn't look like the look of on the face, or that handwriting was a bit bizarre, so we're not going to include that person in the study for no reason, and now it's significant. Isn't that great?
Yeah, also what is very interesting about this, and connecting with the idea of high power also generates false positives, is that when you have high power, for example, huge amount of participants, then every hypothesis or almost every hypothesis could be significant because you have a lot of participants and power. Yeah. Well, so we can go through the last idea, that's that idea of reproducibility crisis. And again, a little question. So replicate studies could help diminish publication biases, and other poor science methods selection. This is true for both publication bias and other methodological bias. True for publication bias only. False, or I am not sure. So let's see. A, true. C, false. Anyone more? A.
You're asking us hard questions, Madeline.
yeah, I want to put you in difficult. Well, considering the data and the computational analysis the authors of these papers done, it is false. This affirmation is false, and we will analyze why. So they give some interesting graphics, but before that, we have to go through this idea that they present as the evolutionary model of science. So they think that science and scientific methods have an evolutionary process. So they begin in some way and then they end in some way and really end. So which are the assumptions of this evolutionary model? So each lab has a characteristic power or the ability to possibly identify a true association. So this power could be higher or lower, depending on different power characteristics. The sample they can go to, and different characteristics. So increasing power also increases the rate of false positives, what we just commented, unless effort is exerted. Effort relating to time, amount of time, amount of activities to ensure that our hypothesis and our all methods are doing, we are proposing it in a correct way, and also looking for high amount of participants and high resources to make sure that we are using an appropriate method. But increasing effort decreases the productivity of a lab or of a group of researchers, because it takes longer to perform rigorous research. So this is like a trade-off again. So we have groups of researchers or labs. They have a specific power. This power can be higher, but to make sure that our results with that power are correct, are true, we need to involve effort, and the more effort, the less productivity. And because the environment is selecting publication amount and what we have already talked about, this effort is not really used, and not really also useful. We are going to see why. So here it is, the first graphic. They say that in this evolutionary model, there are two stages of groups of researchers and labs. So the first stage is that one of science, when the researchers and groups do different investigations. They propose some hypotheses, they do the research, and they communicate, they publish. You know? So that is the first stage. In this stage, the probability of the investigation, so that the probability that a lab have to propose an hypothesis and do an investigation and communicate and publish, is mainly summarizing this mathematical expression, the opposite of the effort. So the high amount of effort, the less probability of publishing. Then the rate of false positives, which is also really important, is related with the power of the lab, what we already seen. So the higher the power, the more probability of a false positive. And we can see this in the graph. So we have in the horizontal x the power, in the vertical x the false positive rate, and these lines which represents the relation at different levels of effort. So if you have low effort, the first one with E equals to 1, then as we increase the power, the false positive rates increase fastly. If we involve a little more effort, then this relation goes diminishing the increase of false positive rates. And then if we raise the effort, then the diminishing relation, it's very high too. But at the end, when the power is very high, the false positive rates also is very high. Then the idea is that communicated results enter the published literature when the groups or the labs do investigations. Labs receive payoffs for publishing their results, and payoffs make their methodologies more likely to propagate in the scientific community at a large scale. This is the first step. So the labs, they have different investigations, they publish more, they get more payoffs. The second stage says that based on these investigations, on these communications, there will be a selection. So first, a lab is chosen to die because different publications drives to different consequences on their payoffs and their results in this sense. They saw that there is a correlation between the age and the fragility. So the oldest labs will die first. But also, age does not correlate with the rate at which payoffs are accumulated. So selection will favor strategies, which I'm just reading, will favor strategies which can increase payoffs most quickly. So a lab at its beginning stages can use some specific methods that gives them the possibility to raise a lot their publications and raise a lot their payoffs. And which are those research methods? Those who can publish more. And those we have already seen that they are erroneous. Does it make sense? Yeah? So we have here another representation of how varying these parameters of power, of false positives, or of false diminishing, or false discovery rate can change, manipulating some of them. So for example, like representing this idea that more power, more false positives, we see in the first graph that as we increase the power, which is the line, the orange line, these are repetitions. So they compute a lot of repetitions of the analysis. As we increase the power, the false positive, both the false positive and the false rate discovery increase. The false rate is, so we have high power, we can discover a lot of things, a lot of positive results. From those positive results, there is a part which is true and another part which is false. That rate of what amount of false results in relation with the whole results is the false discovery rate. So when we increase the power, increases also the false positive results and also the false discovery rate. Then what happens if we introduce the effort variable? So in the second graph, we have the variation of the false positives and false discovery rates when we have effort. So with high effort, the false positives and the false discovery rates are lower. But when we diminish the effort, or we low down the effort, the false positive and the false discovery rates increases. And that happens when labs doesn't involve with effort, when they use that kind of low power studies with less effort to publish. Then what happens with replication, which is the question that I put you at the beginning. Can replication impede this evolution of science, this propagation of science methods? Well, we have at the beginning how these parameters we have already seen can change if we introduce a little amount of replications, which really represents the amount of replications that is done right now. So they saw that 1%, only 1% of the studies which are published in psychology are replications. So if we introduce that and increase it a little, we see the same variation of the variables. The effort decrease, the false positive increase, and the false discovery rate also increase. And we can see it. We can see it when different amount of replication is done, and which are these effects on effort. So we take from the first graph only the line of effort and see how can it varies if we increase the replications. We can see that replication can diminish the effort decrease in labs, but at the end, with multiple replications of the data, we can see that replications have no effect. At the end, the effort goes down. So The conclusion is that original novel results successfully replicated increase the value by 10%. This is a result they saw in their data. So original novel results that were replicated, well done, increase the value of that finding by 10%, and that's wonderful. But when that original results were failed to replicate in replication studies, the penalty was equal to 100 times the value of the initial finding. So there is no incentive to do replication studies, because if I do them and I really confirm and finding of a study, well, it's little value of that finding. But if I do these replication studies and I find something different from the original study, it's really catastrophic for the original study. So there is no incentivization to do replication studies. And well, to finish, just present you a little these graphics, which again relates the replication with payoffs. So we have the replication rate increasing, and then we see how the payoffs are considering the effort. So the blue distribution is with low effort, and the orange one is with high effort. So we can see the payoffs always are higher for low effort, and the replication doesn't change this difference, just a little in the last graphics. Which are the conclusions? So poor scientific methods are the result of incentives for publication quantity, which we already said. Some of those scientific methods involve the misuse of p-values and power considerations. We analyzed the p-values misunderstandings and the power considerations just now. They conclude that if shallower work generating more publications is favored, then researchers interested in pursuing complex questions may find themselves without jobs, perhaps to the detriment of the scientific community more broadly. And looking for solutions, it is not sufficient to focus on guidelines. I brought this because in the last meeting, Tatiana proposed, I was thinking also this thing that maybe if we give more guidelines to researchers to, I don't know, for this kind of misunderstanding and errors, maybe we can change something. And Tatiana also proposed this, but with the results of this paper, we see that not. The focus has to be in the assessment of scientists at the publishing stage. So the assessment of publications. Well, if you have any consideration, any further, I don't know, idea we can discuss right now, you have here some references of interest, and thank you very much for attending the meeting.
Amazing. Thank you very much, Manlan. That's a lot of food for thought. So would the conclusion from the public, from what you've read so far, be that we shouldn't replicate studies?
Yeah.
Yeah.
Mainly, yeah.
Mainly.
Well,
that goes against the whole point of, you know, the replication crisis, right? That we see in psychology. So I don't know if you've thought of any other alternatives.
Maybe the other ones want to ask this too. I can think about something, but maybe the other ones.
Yeah, are there any other questions? So that would be my question. I've got some suggestions as well, so but I want to give you the opportunity.
Okay, perfect. Yeah. So well, the alternatives mainly they talk about this last point about changing the assessment that, for example, reviewers use in the journals to not incentivize false results or just p-value significant results, and mainly to change this assessment, this criteria. This is the idea of the paper. personally, I don't know. I'm not really sure about it. I read several articles about it, and they propose different things. Also, some of them propose guidelines, more guidelines for researchers. But guidelines, we have already a lot of guidelines. So I don't know if they have any effect. Maybe what we've already seen in the last meeting of pre-registering, I don't know if we talk about this, pre-registering the studies could be a good solution. But well, I personally I'm not familiar with pre-registration.
Well, pre-registration would prevent p-hacking, but it wouldn't. It wouldn't. The idea of pre-registration is prevents p-hacking, and it would encourage replication. But your talk today was like, well, replication, might not be the way forward. So this is why I thought it was interesting. It's an interesting debate. I think you're absolutely right. I think just replication alone will just allow us to do more bad science, right? So because the argument is that there's a problem with the rigor of some of the studies at the moment, and that they're underpowered. There might have been p-hacking taking place, the way in which we choose our scientific methods, or the misuse of p-values and power considerations. That's what I'm talking about. So if you just replicate that stuff, then obviously we're only replicating bad science. The question is, how do we replicate good science, right? And so this is where I think one of the ways forward is we should think about replication as a replication and extend kind of thing. So you replicate a study, but you highlight the issues with that study, and then you replicate it, but with more rigor. So if you think that they've used their sample size was too small, for example, or they used the incorrect analysis, you would pre-register your study to say, I'm going to replicate this study, but I'm going to change X, Y, and Z to see if it makes a difference. So you first replicate and then you extend the study, making it better.
Yeah, it makes really sense, but do you think it really be incentive? So what we are
yeah, that's a very good point. That's what should happen. Now the question is, right?
Yeah, of course. Yeah.
What are the incentives then for making that happen?
So the idea of the paper, it was that replication are not good suited for our way of doing science now, but they definitely have their interest.
Yeah. So I think I think the incentives is, if you take the p-values away, so it's no longer about only publishing significant results, and that's where pre-registration comes in, right? If you pre-register your analysis, your ideas, it shouldn't matter if it's significant or not. What matters is the findings you've got from that, and if you do a pre-registered study, then it should be automatically accepted for publication. And I think that's a good incentive in terms of the fact that you can still have lots of papers and good papers if you pre-register them, right? So that's kind of where the idea of pre-registration comes from. Yeah, and I really think these are good. It touches on other things around ethics. What I see in the UK a lot is a lot of our psychology undergraduate students and education undergraduate students, they do a dissertation, okay? And they do research with children or with small populations, or, even with other undergraduate students sometimes. Then they write up their dissertation. Some of them have good findings. Some of them, the rigor is a little bit lacking. But none of that data ever comes to the surface. None of that data is ever published. And I think there's an ethical issue there in terms of, we do research, which is a waste of time, right? Just so someone can graduate, but it's seen as practice, right? And I would then argue, why don't we just ask students to replicate and extend, because I think is the second part, replicate and extend, the extension part is important. Why don't we ask them to do more of those kind of studies, so we improve science? They can publish their results much easier because it's, a replication and extent if it's pre-registered. So they get all the good practice, and we actually help science, because what they're doing right now is very often when students come up with new ideas, it's pilot studies, the idea is there, but it's not quite clear yet what the methods are. And that's why that researchers. So I think asking students to do a replication and extend study as part of their training is probably the best use of science, of our time, and ethical point of view.
Yeah, could be very interesting also, because you have the previous study and you have the ideas there, you have the method, so you are not working in the
Yeah, and you still need you're still training critical analysis skills, because the problem is you need to extend, the question is, should you just replicate it, or should you replicate and extend it? You still need to do a very in-depth critical analysis of that study to know what is it that you need to extend on, in what way should that study be, where were the flaws, methodologically speaking, to extend it.
And I also was thinking about that, like extending research, like replicating and extending prior studies. Like I like the point of Madeline saying that, like, the change has to come from within the scientists, from the persons. Like if I did a study where we replicated and extended an intervention, and then the peer reviewers said that, oh well, okay, yeah, so you've replicated this, so this has been done priorly, so I don't think that this should be like published. And we had argued in the paper that we actually extended methodologically the findings, and that's why we wanted to publish it and conduct the study. So I think that it's very important point that we have to, when conducting research, we as researchers have to change how we like give feedback, or how we evaluate science or something. That just a thought about it.
Yeah, this idea of innovative work always, and not replication ones.
Yeah, or you perhaps run into the exact opposite issue of what Terje just described, that you have an adaptive or maybe extended replication, and you get the feedback of, well, this is not really a replication anymore, is it? Because you added things to it and you made changes. So how could you then even still compare, even if you maybe point out that, well, it is a methodological change because there were issues with the original study. So that is then just a problem as well, I would say, on the side of understanding of what is replication and what does it want to do. But we, of course, then run into the dilemma of what can we do as researchers that want to publish versus those researchers of us that are sitting there and maybe giving reviews, and that can have an impact on that side. So I guess that's kind of a bit conundrum that we have of what can both sides do to incite a change perhaps here, because we all know that even though maybe you don't want to use certain things, or the p-value is not really what it is used like in science, we will still most likely reference it in our works if we want to publish something, because it's the standard that is set, and it would probably look rather odd if you would try to avoid it. So you could just perhaps add to it, but would also need to justify, why are you talking so much about power, for example? Or then if you think of something that comes up quite a lot in terms of critical thinking as well, at our uni, where students are usually asked for their final dissertations as well to consider issues with Cronbach's alpha. So if you're having a questionnaire and look into that, it is very commonly referred to if you want to publish something. But again, just like the p-value, not really in the way that it was ever meant to be used, or not in the way of what it should actually express. So it is still something that you will be asked to potentially reference as soon as you include a questionnaire in your work. And then you stand there in a dilemma yourself if you want to publish something. So we need to kind of have an
just to clarify, we're not saying you can't use p-values.
No. I get that, but I'm just saying it's of course kind of a dilemma from all sides. So if you want to publish, of course, how do you do it in a meaningful way, perhaps, instead of just meaninglessly using it on in a way that is not intended to be used.
No, absolutely, that's the point. Yeah, and I think with the replicating sentiment, it's a very good point you make there. And I don't think it's entirely clear yet, but the idea would be something like you replicate it identically and then you extend it, right? So if you say the measure isn't valid, you would then replicate it with the existing measure and with a new measure to then see if the newer measure is better. Or if you say there's a problem with power, you would first replicate it with the original sample size and then you extend it to see what would happen, right? If so. But indeed, there aren't clear guidelines yet around what all these things would look like. So I think that's where guidelines could come in terms of better practice when it comes to these issues of replication and extension. What is that? What are those animals basically, and what is best practice within extension? How far do you go in an extension so that it's no longer a replication, for example? Right. I've seen it's time. We're past time. I want to thank Mandolin for a very great presentation of the paper. I think it's very helpful. And thank you all for joining us. And hopefully see you again at the next one.